Welcome back to Let's Code. Today we're diving back into state machines with statig. I don't know how to pronounce that. How do you pronounce that? Static is a new library that came out, I don't know, 13 hours ago, something like that. I've been through the README, I've been through the examples. I think today what we're going to do is take a look through the README and sort of give an overview of this kind of state machine approach and not necessarily compare it to other state machine libraries, but explain what this state machine library in particular is about and how it views the world or how it expects you to interact with it. Because depending on how your state machine library is built, will tell you a little bit more about how it's expected to be used or how it expects you to move from state to state. So right off the bat, we've got statig is a hierarchical state machine. This means that you can have states nested inside of other states. So what you end up with is something like a tree where you've got all of the root states, and then each of those root states can have different states inside of them, or rather below them in the tree. You don't have to use it like this. So if you've got a simpler state machine, you don't have to use this, they call it super state functionality, but it is there if you need it. It also includes state local storage, which is very interesting. And the implementation, I think, is actually super interesting for state local storage. What this means is that you don't have to have one struct that holds all of the fields for all of the things that all of the states access. So you don't have to end up with a state machine that has 5 optional types because you've only got one required field and 5 things that are accessed from different states. So this allows you to put those optionals as actual types instead of the optional type, or the root type that they are instead of the optional type, inside of just the state that cares about them. It's no standard compatible, which is really interesting. And some of the examples that they use actually are for blinking and LED. So that would be something that would be really interesting to throw onto the microbit. We went with a microbit v2 for the Rust embedded work that we were doing. And I wonder if this state machine implementation could be a way to interface with the LEDs on the microbit. And then the last feature here is some macros. So this is a very macro heavy library, but they also officially support not using those macros. I haven't extensively used this library. Obviously, it was released 13 hours ago. So I can't tell you what the errors will look like if you use the macros, but quite often a reason for not using macros would be getting easier to explain error messages. That said, the macros do reduce boilerplate and make it a little bit easier to work with, especially when you're writing state machines for the first time. So we'll cover a basic example. We'll go over some of the concepts that statig wants you to understand, and then we'll very briefly touch on some of the implementation details. I don't think we're going to actually get into the examples, so I might make that a different video, especially since the examples that I saw in this repo can be a little bit more confusing than not, because they do things like take an event that doesn't have any fields and automatically swap between 2 states, which kind of cuts out a lot of, I think, the real world implementation that would exist there and makes it a little bit harder to understand. So to start out, the first implementation of a state machine that we're going to see is going to be controlling the status of an LED. So this LED is either going to be true or false, so we can treat that as kind of like on or off. And this blinky struct is going to be the thing that holds our state machine state. So the state that everything has access to, or a context, or whatever you want to call it. There is something specifically called a state inside of static, so I don't really want to use that word for this, but it is a struct in which we can store data that is accessible to every state that our state machine can be in. Then we've got an event, and the implementation of state machines for static is really interesting because it kind of expects you to just kind of throw events at it, and then it will handle dealing with those events. So the implementation here is a little bit more like you have a lot of events coming in from foreign places, which is one of the reasons that I thought that this might be really good for Bevy for the 2D platformer example that we've been working on. Because in the Bevy case, we could have a bunch of events that fire off anytime you log an input, for example, right? And those could be controls that flow in and get processed by the state machine, and then you can kind of make sure that you're not going from a state that you want to be in to a state that you don't want to be in if a lot of events get sent very quickly. The impulse state machine is the trait you have to implement for the struct that will represent your state machine. State is something that, as far as I can tell, gets generated, so it's not actually in this code. Same thing with superstate. Superstates are the parent roots for your state. So the places that state gets held are typically in the leaf nodes of the state machine. So they'll be at the bottom of the tree in the leaves, which means that if you're in a state that is a parent or a superstate, those states will borrow data from the leaves where the state is held. That's why we have a lifetime here in this associated type, although we aren't using it in this particular example. The event here is a, like I said, unit struct. So these events are going to come in and we're going to process them to determine which state we should move to from the state that we're in. And this specifically is one of the reasons that I felt like these examples were a little bit confusing, because you can see if we go lower that the event actually isn't used anywhere except for when the state machine should handle some event. So we'll get into that in a second. But suffice it to say that this state machine in particular takes just events, generic events. They're just an event. They are not any specific kind of event. Although you can make this, as far as I can tell, whatever you want. And then finally, in our impl state machine, we have to specify which state we're actually starting off in. So in this case, we start in the off state. And this is where we start to get pretty macro heavy. So these macros are written like this. They basically function as derived macros, but they're not written as derived macros. So they're basically only reading your code and generating some other code. They're not really manipulating any of the implementations that we write here. They're doing things like reading the arguments that we're passing in and stuff like that. The reason these are written as attribute macros instead of derived macros is that you cannot put a derived macro on an impl block. So they have to be attribute macros, even though they function the same way that a derived macro would. So we've got these associated functions on blinky, and we can define states as well as actions. Actions we'll get to later, but basically we've got an on state here and an off state represented by these functions. And whenever we get an event, we have to return a response. A response is one of three things, one of which can be a transition. So in this case, if we're in the on state and we receive an event, then we're going to turn the LED off. Remember, this self is the struct that we defined earlier. So it's this blinky LED. Then we can return the transition here so that we can transition into the off state. And you'll notice that the function call here doesn't match this function signature. So we aren't calling that function here. This is impl on blinky, whereas this off function is on state. And state is something that is generated out of these attribute macros for us. So it can be helpful when you're first looking at these examples to actually look at the expanded macros and see what code is actually being generated. Similarly, in the off state, if we receive an event, we're going to return another response. In this case, we'll turn the LED on because we have a mutable reference to self, which holds the LED field. And then we transition into the on state. So we turn the LED on, we transition into the on state. And that's all of the code we absolutely have to write. So we've got our main function here. We define our state machine as mutable. We set up a default blinky. We call state machine init, which initializes our state machine in the state that we defined as the starting state. And then we can start passing events into it. So the state machine will handle this event. The event, of course, doesn't have any fields or anything on it. So it's just a unit struct where just an event happened. Depending on which state we're in, one of these two functions will get called. It will handle this event. If it's on, it'll turn off. If it's off, it'll turn on, and it'll transition us into the other state. So we can look a little deeper at how to construct these states and effectively event handlers. For example, we have an on state here. We use the state attribute macro on the on function. It accepts the event. We have to return a response. In this case, it's another transition, but we actually have three different things we can return from this function. We can say, hey, the function has been handled. Don't do anything. So we can stay in the same state. We can transition to a different state, or we can do something that's a little bit more complicated and a little harder to understand right now. We can defer the event to the next superstate. So remember, superstates are like parent states. And superstates, of course, come with their own macro. So we can define a superstate on the same impl block that we just used on blinky. It has the same function signature, so we get this event and we return a response. In this case, our event is an enum. So we've got timer elapsed and button pressed variants. If we get an event that is a button pressed in the playing superstate, then we transition into paused. So you can imagine this as being like a Spotify player. If we are currently playing a song, the event comes in. We are only matching on events that are the button pressed event. we can then transition into the paused super state. And otherwise, we can just say, hey, yeah, we saw the event. It's handled. Don't worry about it. But that means that we also have to define the states that are under that super state somehow. So we can do that using the state attribute macro once again. We have the state attribute macro. We can specify the super state of this state. So in this case, that's playing, which we defined here as a super state. So on is a substate of playing. So on can also receive an event and respond to it. In on, we match on the same event type. So we've got timer elapsed or button pressed. If the timer has elapsed, then we transition into the off state. If there's a button pressed, we pass that event up to the super state where it can be handled. And of course, super states can have super states. So you can get basically as complicated as you want out of this tree of states. Actions, I feel like, are super important because it allows you to encapsulate logic that needs to happen when you enter or leave a state. So in this case, we've got an entry action, enter on, and an exit action, exit on. So we can have a state called on that receives the event and returns a response. When we are in the on state and we receive any event, we will transition into the off state. But when we enter the on state, we can use the action attribute macro to print out that we've entered the on state or we've exited the on state in the same way. So we've got states. Those states can handle events. Those states can have super states, which are sort of like parent states. We can determine which of those two substates or superstates is going to handle a given event. We have 3 ways to handle an event. We can either transition, we can just say, okay, it's handled, great, or we can defer it to be handled by a superstate. They mentioned context in the README, which is just this self argument. All this means is that you can access the larger context, so that blinky struct, in any of these. So you can access it in a state, a superstate, or an action. State local storage is super interesting to me because the implementation here is basically only specifying that there's an argument here that is a mutable reference to some value. This is almost very similar to the way that Bevy will do a local state without having to actually specify that it's local state. So because we aren't calling this function ourselves, the macro, the state machine macro, can read this function when we define this as a state and say, hey, there's an argument here that's a mutable reference to a U32. We'll keep that state around, and anytime this function gets called, we'll pass that U32 in as a mutable reference. So as is typical, we can accept an event when we're in the on state. We can match on that event. In this case, if the timer elapsed, or we match on the timer elapsed variant of the event, then we're going to subtract 1 from the counter. If the counter is 0, then we'll transition into the off state. Otherwise, we'll just say, okay, it was handled. We adjusted the counter, and we can accept the next event. We can also handle any other events. So in this case, if a button was pressed, we can transition into the on state with a value of 10. So that would set us up in this on state with a counter value of 10 that would then count down anytime the counter elapsed. It's notable that the local state is only mutably accessible in its local state. So in this case, it's the on state. But you can also access it in any actions that are associated with that state or any superstates of that state. And I really like this visualization that they have here. So if we have some state machine, it can define a tree where we have a superstate of playing and a superstate of paused. Playing has a reference to the counter because the on state defines that counter, like we just talked about. So playing can access that counter, but paused cannot. And this is roughly how you model states and substates. So inside of playing, we can be on or off. Once we're in paused, we can only be in paused. And if the generation of the state enum isn't quite clicking with you yet, here's an example of what that would look like in our example. So our state can be on, off, or paused, and the on and the off both have some local state called a counter that is a usize in this case. So this enum represents all the states that we can actually be in. Because remember, if you're in the playing state, you have to either be in on or in off. Notably, when we were talking about deferring events, an event that comes into our state machine will first get passed to the leafmost node. So it'll get passed to on before it gets passed to playing, for example. If you defer it all the way up to the root theoretical top node, then it will just mark that event as handled and move on. If we look back at the graph again, you can think of the transition order and the exit and entry actions being called as going up the tree and back down. So if we're in the on state and we transition into paused, the exit action will be called on, then the exit action will be called on playing, then the entry action will be called on pause. So you can go up the tree, calling the exits, and then down the tree, calling the entries. So I always get hyped up about new state machine libraries. I know that maybe not everybody shares my excitement, but anytime I see one, I love to go through them. So I hope you enjoyed the video, and we might see more of this library in the future, depending on which state machine we choose to use for our bevy games. And I'll catch you in the next video. Have a great day.